Hey everyone, this is Bhargav Sudhar, and today we will discuss about tree. What is a tree? So in this today's session, we'll specifically learn about the introduction of tree, then some other definitions. Okay. So first, let us understand what is a tree in this mathematics. So a graph. First, let us understand what's an acyclic graph. So a graph is acyclic if it has no cycles. So just by its name, acyclic means it has no cycles, okay, or no circuits. Both are same. So a graph is known as acyclic if it has no cycles or if it does not have cycles or circuits. Now, a tree. What is a tree? It is a connected acyclic graph. So that means the graph has to be connected and as well as without circuits or without cycles. So in other words, a simple connected graph without circuits is known as tree. Why simple? Because it has no loops. Fine. Now let us discuss examples. So consider this type of graph. So as you can see that we don't have any we don't have any cycles, and as well as it is connected, so it is a tree. Now in same manner, this is also a tree. So as you can see that there is no cycles and as well as it is a connected and simple one. Fine. Now a graph without cycles, it is a forest. A graph without cycles, it is a forest. Thus the components of a forest, okay, so obviously a forest is larger. Fine. So forest contains tree in our general language. So graph without cycles, it is a forest, and the components of the forest are trees. So that is, forest is what? It is a collection of trees, or to be specific, collection of disjoint trees. Fine. Now for a tree, the vertex of degree 1 is known as a leaf. Okay, so a vertex having degree 1, it is known as a leaf or terminal or what? A pendant vertex. So all three are same: leaf, terminal or pendant vertex. Now a vertex of degree more than 1 is known as a branch node or internal node. Okay, so we have two categories. A vertex of degree 1 is known as leaf, terminal or what? Pendant vertex, and having more than degree 1, okay, so it is known as a branch node or internal node. Let us discuss example. So as you can see that in this example, first it is a tree, right? It is a tree and it is connected one, and obviously as it is a tree, we don't have cycles. So as you can see that we have total like 5 vertices. So this degree of A, now we all know what is a degree of A, okay, and if you don't know, just go through the previous videos. I think first three parts. Okay, so A, it has a degree what? 1, D has degree 1 and E has degree 1. So what we can say that this A, D and E, they are leaf or terminal or pendant vertex. Now just consider this B and C. So B has degree 3 and C has degree 2. So they are more than 1. So that means this B and C are what? Branch node or terminal node. So this A, D, E are leaves, whereas this B and C are branch nodes. Fine. I think it is clear. What are the properties of trees? So G is a tree if and only if there exists a unique path between every two vertices of G. So we have this property. G, it is a tree if and only if there exists a unique path between every two vertices of G. So that means if it is a tree, there exists a unique path between every two vertices of G, and also converse. So if we in a graph there exists a unique path between every two vertices of G, then we can say that it is a tree. Fine. The second property is G is tree if and only if what? If G is connected and has exactly n-1 edges, where what? N is the number of vertices of G. Fine. So if a graph is connected and has exactly n-1 edges. So suppose we have graph having what? Having 3 vertices, and having 3 vertices, and if we have number of edges are what? n-1. So that means 2. So it is a tree. So just imagine just having a triangle except what? And remove one edge. So that means this V-shaped graph. So it is a tree. Why? Because it has 3 vertices, 3 minus 1, that is 2 edges. So it is a tree. And conversely, if it is a tree, then this holds. So if it is a tree, then it is connected as well as what? It has n-1 edges. Okay, so this will be useful. Now let us understand what is the eccentricity of a vertex. So the distance between two vertices in a connected graph, it is what? We discussed this in, I think, previous session. So in a connected graph, there's the length of the shortest path between them. Fine. Now the what is the eccentricity? So eccentricity, it is denoted by this E of V symbol of a vertex V in a connected graph G. It is what? The maximum of distance of UV of all U in G. Okay, we'll learn. So that is what? This eccentricity of V, of a vertex V in a connected graph. It is what? The distance from from V to the vertex farthest, not shortest, the farthest from V in G. Now let us discuss example. So yeah, this is the notation. Now consider this graph. This A, B, E, D, C, F, G. So what is the eccentricity of A? So that means distance of what? The distance from A to the vertex farthest from A in the given graph. So as you can see that this we can reach from A to B. So eccentricity, not eccentricity, the distance is 1. So we need to find the what farthest distance from A to any vertex. So what is the maximum distance, farthest distance? So we can go from A to B, that is 1. Now A to C, that is 2, and A to F, 3. So I think this is the farthest distance. We can go from A to E, so that is 2. The distance is 2. Now A, B, B to C, C to F, or C to G. So the farthest distance from A to F, it is 3. So the eccentricity is what? 3. Of A is 3. Now, okay, fine. So it is 3. Now what about B? So we can go from B to E, that is 1 distance. B to C, that is 1. Now B to F, so that is 2. So the maximum distance, the farthest distance is 2 here for B. Okay, so eccentricity of B is 2. Then C, eccentricity of C. So C to F is 1, C to B is what? 1, and C to A is 2. Or C to E is also 2, C to D is also 2. So the farthest is 2. Okay, so eccentricity is 2. Now for D, consider D. So for D, we have eccentricity is 3. How? D to B, B to C, C to F, D to B, B to C, and C to G. Okay. In same manner, the eccentricity of E, it is 3. How? E to B, B to C, and C to F. Okay. And what is left? That is F and G. In same manner, F and G. Obviously, it will be either A or E. But the farthest distance is what? 3. So eccentricity of F and G, they are 3. Fine. Now what is a center of a tree? So a vertex with minimum eccentricity is called a center of G. So I think consider this example. Here the minimum eccentricity is what? That is B and C. Minimum eccentricity of B and C is 2. So both B and C can be the center of a tree. Fine. Now what is a m-ary tree? So an ordered tree in which every branch node has the most m sons is known as m-ary tree. We'll understand in by figure. Now an m-ary tree is known as regular m-ary tree if every branch node has exactly m sons or no sons. Okay. Now consider these two graphs. Okay. So what is m-ary tree? If every branch node, now we know what is a branch node, a vertex having more than one degree. Okay, branch node has the most m sons is known as m-ary tree, most m sons. Fine. And what is a regular m-ary tree? So that means it has exactly m sons or no sons. So just consider this graph. So as you can see that here we have total 4 degree. Okay, and here we have total 4 degree. Fine. And here it has what? 3 degree, and here this vertex has what? 4 degree. So what is the difference? So as you can see that here it has what? 4 sons, and here also it has 4 sons, and here 3 sons and 4 sons. So the first figure is what? It is the case of regular m-ary tree or regular 4-ary tree, because we have exactly 4 cents. Fine. And here we have 3 cents and 4 cents. So it is and the most cents are what? 4. So it is a 4-ary tree, and the first one is regular 4-ary tree. Fine. Now what is a binary tree? This one is important. So an m-ary tree is known as a binary tree if every branch node has what? At most 2 cents. Okay, at most. Fine. So the maximum can be 2 and minimum can be 0. So at most 2 cents. And in same manner, regular binary tree or full binary tree if every branch node has exactly 2 cents or 0 cents. So consider this graph. So this has 2 cents, this has 2 cents, and this has 1 cent. But most is what? 2. This has 2 cents and this has 1 cent. Fine. So this is a what? This is a binary tree. Fine. So consider this graph. Now this has 2 cents, this has 2 cents, this has 2 cents, and this has no cents. So this has exactly 2 cents or no cents. So it is a binary tree, but to be specific, it is a regular binary tree or a full binary tree. Fine. So as we discussed, first figure it is a binary tree, whereas the second one it is a regular binary tree or a full binary tree. Fine. Thank you.